Thank you very much, Nick, and thank you for attending this session, especially after such a wonderful lunch. I know it's a challenge. It's a privilege and an honor to be here and to have the opportunity to present this talk on behalf of my co-author, Yeonjung Liu from RSC, Scott Halley from Mineral Mapping, and a whole bunch of people from Zenith Minerals. Key messages of this talk: Red Mountain is a recently discovered gold deposit in the Auburn Arc, which forms part of the New England origin, which in turn belongs to the Tasmanites in eastern Australia, which is known to be a very prolific mineral belt. The discovery, I call it, was the result of classic exploration and targeting, involving just, like proper, solid geological means of exploring and targeting and discovering this deposit, which is pretty cool. However, the understanding of this deposit is still somewhat incomplete, and I'll show you why. And the various affinities that are listed there that people thought this was related to. And that obviously is then difficult to define exploration parameters and target these things properly if you don't understand what you're actually targeting. And so we, RSC, assisted Zenith in gaining an improved understanding of this deposit and future exploration by carrying out an integrated review of lithological and petrological and geochemical parameters, and I'll take you through that in a bit more detail. So where are we? The Red Mountain deposit is in the southern Auburn Arc, and it's bracketed by two world-class operating gold mines, hence the prolific nature of this region. And it's basically an Andean-style magmatic arc that formed in the late Paleozoic to Triassic. And as I said, think of it like the Andean margin in South America. The Red Mountain project itself occurs in the Caledon granodiorite, which forms part of a multi-phased massive batholith. This is all these different colors there on the screen. And it's in turn intruded by the Tacoma, granite of unknown age, and that's important, keep that in mind. And there's also a bunch of other dykes coming through this. So this is a big intrusive activity, a center of activity there. Red Mountain itself sits on the contact between the Tacoma and the earlier Caledon granite. All right, believe it or not, but Zenith initially target this area and explored it for manganese oxide and cobalt. And geologists on the ground taking samples from rock chips, and they turned out to contain elevated gold as well as elevated silver and a whole suite of other minerals, or elements, I should say. So on the back of that, a soil sampling grid was devised along here, as you can see on that map, plan view there. And the soil sampling confirmed a zone of anomalous gold, as indicated by these color-coordinated contour maps there. And the interesting thing is that you can see from the slide up there, the bullseye anomaly in the center of a circular feature that is defined by these anomalies of arsenic, gold, antimony, and other things. So that's really interesting, and that was essentially discovery, or the origin of the discovery of the so-called Red Mountain igneous complex in 2019. And on the back of that, more work was done in terms of mapping, more sampling, and that confirmed the presence of a essentially circular breccia pipe, a diatreme, fringed by this tufaceous to siliceous pipe that forms this circular feature, and you can actually see that in outcrop quite well. And you also have these radial rhyolite dykes emanating out into the countryside. That's also important to remember. Further mapping, airborne EM and IP confirmed the presence of a potentially quite significant magmatic hydrothermal system, and drilling on the back of that. This is a chargeability diagram of that area, and it beautifully highlights that circular, the ring-like nature of that diatreme with this bullseye low in the center. And that is also quite important in the context of this. But the company was basically scratching its head asking, what are we looking at here? The area or the region is known to host world-class porphyry systems as well as gold systems in the form of, say, Krakow, for instance, which is a low sulfidation epithermal system. There are skarns. It could be structurally controlled orogenic gold. These trends that you see here, they're not artifacts. There are a series of northwest-southeast trending structures going through there. What is it? And that's when they came to us and asked us to help them with constraining and better understanding the relationship of and the petrogenesis of the associated igneous rocks. Do they in any way relate genetically to the gold that we're seeing here? And by doing so, ascertain the nature of the mineral system and the most probable style of mineralization, because that obviously, again, has implications for future targeting and exploration, and provide vectors for exploration targeting the system itself. As you saw, the metal zonation is quite well developed across the deposits. You can use that for vectoring and targeting. And the other thing is that the whole system is still pretty much intact and upright. It's not that old. It hasn't been dismembered. That helps too. And so on the basis of that, we basically did a comprehensive review of all the existing exploration data, reassessed the petrology and all the logging information from about 60 holes that they drilled since 2019, and in particular do an in-depth assessment of multi-element lithochemical data. The reason I'm telling you all of this is, yes, it's in Queensland in Australia, which is far, far away, but this is extremely applicable to the Arabian Shield and works just as well here. And it's a really cool and powerful technique of combining multidisciplinary data and especially powerful lithogeochemical data for the purpose of identifying, constraining, and developing ore deposit models for targeting and exploration targeting purposes. The first thing that hits you when you look at the core, which is what we did in the first instance, you have various igneous units, and when you look at the gold distribution across these, there are these rhyolite dykes where the gold is disseminated, and these have intruded granites and granodiorites where the gold occurs exclusively, more or less, in vein, fracture, quartz vein related structures. Okay, so that tells you something about the timing relationship. And the same, here's another example. Again, the rhyolites look quite different from the granite and granodiorites, and the gold occurs in different association within these. On the basis of the petrology and the lithogeochemistry, we're able to distinguish 6 mappable magmatic phases. That includes 2 post-mineralization mafic dykes, these 2 types of granite and granodiorites, and 2 types of rhyolite dykes, one mineralized, the other one unmineralized. And you look at these elemental ratio plots, you could be forgiven for thinking, oh, that's just a classic differentiation trend. As your magma becomes more differentiated, more felsic, you basically dilute the whole thing, the system, with silica, and all the trace elements regress to 0. But there's a lot more to it, and I'll show you this now. The granodiorite and granite experienced hornblende fractionation when you use a Lauk-style classification diagram, such as this one, vanadium over scandium over scandium. And what happens is, with hornblende fractionation, you suppress the formation of feldspar, you fractionate out the hornblende, and that tells you you're dealing with an oxidized, water-rich, porphyry, copper system, fertile magma. And that applies to the granodiorite and the granite. However, if you have a look at that plot here in the upper right, the rhyolites, they plot in the complete opposite direction into the magnetite to ilmenite series, which means they're derived from reduced intrusions, nothing to do with the granodiorite and the diorite. That's really important. Moreover, the rhyolites also have a completely different zircon fractionation trend when you compare them to the granodiorite and diorites. These different types of magmas couldn't have derived from the same parental magma, which is what you want to see in a porphyry system that fractionates and continues to fractionate, and the final phase is what then is the causative pluton for your porphyry copper mineralization. Furthermore, all of the samples, or the material, these magmatic phases, except for the mafic dykes, again, when you use Lauk's style classification diagrams, diagnostic diagrams such as these ones, that tell you that the magma, not just from the rhyolites, but also the granodiorites and granites, are derived from a metasomatized mantle source. Graham Beck said the other day, gold-rich fertile melts are special, and these ones are. So that's also very important. Basically, it tells you you're dealing with a fertile, mineralized system. It still doesn't necessarily tell you what kind of system, but I've already told you earlier, can't be porphyry, it's got to be something else. And then the final nail in the coffin of the porphyry theory is the alteration evolution, when you use this kind of diagram. And you look at the trend from the least altered to the most altered rocks, again, where the rhyolites are. This is dominated by sericite alteration, not the kind of phyllic, probalytic, potassic alteration you'd expect to see in a porphyry system as you get closer to the ore zone. And then finally, if you look at Pathfinder cumulative frequency plots, these rhyolite dykes, the red in particular, the mineralized rhyolite dykes, are all anomalous with respect to these elements that I've listed here, except one, and that is moly. Moly with respect to molybdenum, and you remember that bullseye anomaly, which is separate from the gold anomalies, that's basically the proof of why that is. The moly is associated with the granodiorites, everything else is in the rhyolites. Again, rules out a porphyry. And then just to put all that together, and I won't go into detail, essentially you're asking, is this a porphyry? No. What is it? It's associated with reduced stocks, small things that are much closer associated with what you expect to see in an intrusion-related gold system. Also in terms of their tectonic environment, which I don't have time to go into, but you can use that and reverse engineer it and constrain the tectonic environment this thing formed in, which is very useful again for targeting purposes at the bigger scale. So putting all of this together, this is what we came up with in this work with Zenith. We're dealing with a gold, bismuth, antimony-rich or enriched assemblage that is representative of the cooler, or in other words, outer portions of a causative intrusion-related system, a pluton at depth. The geochemical data that we looked at points to that source, that causative pluton, at depths below the mineralized rhyolite. This is the same view here. That's a cross-section of where the drill holes are looking north, and this is a sort of a stylized diagram of what we're looking at. So here's the diatreme, what they were drilling prior to us coming in, looking for that porphyry, that elusive porphyry. We're saying the mineralized rhyolites, they're over here on the western flank of this diatreme, which means your fertile, your causative pluton is somewhere down there, and it's not associated with the diatreme. And we use the analogy of Mount Wright, which is an intrusion-related gold system in the Tasmanites, in the New England origin, further to the north, near Townsville. So fairway north, but it's exactly what we're looking at here. And the cool thing is that at the moment, the Zenith drilling is up to here somewhere. Mount Wright doesn't start until 200 meters below the surface, but then it goes down to a depth of more than 1 kilometer. It keeps going. And that's what's really exciting about this project. And so we told Zenith, stop drilling the crap out of the diatreme, go over here, step out and drill underneath this area where we think this causative pluton is. And last month, they did exactly that. They drilled here, and this is what they announced on the 11th of September. 140 meters of over 1 gram of gold. Concept proven. Really cool. And last week, they released another announcement where they drilled a second hole. So this is the hole I just showed you. Here's the most recent hole, and they just got the assays back and released them last week, and you can see it over there, over 325 meters of 0.6 grams per ton, which is exactly what you expect to see in an intrusion-related gold system. So in conclusion, the lithogeochemistry and petrography that we did defined 6 mappable magmatic units at Red Mountain. The granite and the granodiorite are most likely co-magmatic with the collodone granite, which has been dated at 260, so late Permian, early Triassic. And these guys are derived from an oxidized porphyry copper fertile magmatic system. And they do show a degree of fertility like I showed you. And that bullseye moly signature is also a representation of that. But the thing is, these granodiorites and granites, they're not necessarily that porphyritic. What that tells you is that you're probably already too deep in the system. In other words, there was a porphyry there, but it's been eroded away. And what we're looking at is the root system. All the good stuff's gone because it's been eroded away, uplifted, gone. However, there's a younger phase of magmatic activity, gold fertile magmatic activity, that might post-date the collodion by up to 30 million years. We haven't dated it yet, but we will. And these are associated with these mineralized, unmineralized rhyolite dykes that are characteristic, indicative of a metasomatized mantle source, a gold-rich mantle source, unrelated to the granodiorite and granite, but similar to gold fertile magmatic suits elsewhere. And they're enriched in that the association that is up on the screen there, and they all confirm that close association of these dikes with a reduced intrusion-related gold system that was telescoped into this older porphyry system. So lightning struck twice in that space, and that's not uncommon. You see that in the Andes and other places a lot, and that's a good thing because it enhances your metallogenic potential of that area. And it is analogous to Mount Wright, and that was a great news for the company because they can basically go, we have this potentially world-class system at our, at hand there. The point again is that lithogeochemistry combined with petrology and geophysics can be an extremely powerful tool for the purpose of not only targeting, but also constraining your ore deposit model and gaining a good understanding of what it is that you're looking at, that you're targeting in the bigger to prospect scale. And I won't have time to go into this, but it basically also demonstrates that this area is not only fertile and has potential for a one period in Earth's history, but a younger one that until now had been pretty much ignored. And this is exactly, again, what you see in the Andes, these phases of when things happen due to plate tectonic processes, reorganization of plates, change in far field stress, and all the rest of it. And that is all important to consider. And that's exactly what's happening here in the Arabian Shield. And we're still learning and gaining better knowledge of all of this. Thank you for your attention.